What defines the true edge of our solar system? For many years, this question was treated almost like a matter of distance, as if one could travel far enough past the outer planets and simply arrive at a final boundary. That assumption, while intuitive, turns out to be incomplete. As spacecraft began to move farther from the Sun than ever before, particularly through the Voyager missions, scientists were given something far more valuable than theory. They were given direct measurement, and what those measurements revealed was subtle but profound. The solar system does not end at a fixed location. It fades, interacts, and reshapes itself through forces that cannot be seen, only detected. Voyager 1 and Voyager 2, launched in 1977, were not originally designed to answer this question in full. Their primary mission was to study the outer planets, yet as they continued their journey into deeper space, they became instruments of a different kind of discovery. They began to approach a region where the influence of the Sun no longer dominates completely. Now, let us pause for a teaching insight. When we speak of the Sun's influence, we are not referring only to gravity. Gravity extends much farther. Instead, we are referring to the Sun's energetic environment, particularly the stream of charged particles it continuously emits. This distinction is essential because it changes how we define a boundary in space. As Voyager moved outward, its instruments detected gradual changes. Particle speeds shifted, radiation patterns altered. The environment was no longer behaving as it did closer to the Sun. These were not abrupt changes, but they were consistent enough to suggest that the spacecraft was entering a transitional region. This leads us to a crucial realization. The edge of the solar system is not a line you can draw on a map. It is a region shaped by interaction, where the Sun's outward push begins to encounter resistance from something beyond our system. And this raises the next logical question. If the boundary is not defined by objects, then what exactly creates it? To answer that, we must examine the force that extends the Sun's reach far into space, forming the structure that surrounds everything we call our solar system. That force is the solar wind. To understand the force that defines this boundary, we must now examine something the Sun is constantly doing, even though we cannot see it directly. The Sun is not silent or static. It continuously releases a stream of charged particles, primarily electrons and protons, into space. This outward flow is known as the solar wind. This solar wind does not travel in a narrow beam. It expands in all directions, moving outward at speeds that can reach hundreds of kilometers per second. Over time, this persistent flow creates a vast region around the Sun. You may think of it as an extended atmosphere, but far more diffuse and energetic. This region is called the heliosphere. Here is a useful way to understand it. Imagine a steady wind blowing from a central source in an open field. If there were no obstacles, the wind would simply spread endlessly. But space is not empty in the absolute sense. Beyond our solar system lies the interstellar medium, a thin distribution of gas, dust, and charged particles that exist between stars. As the solar wind expands outward, it eventually begins to encounter this interstellar medium. At that point, something important happens. The outward pressure from the Sun meets resistance from the galaxy itself. The solar wind slows down, its behavior changes, it no longer moves freely. Voyager spacecraft provided direct measurements of this effect. As they moved beyond the orbit of Neptune, instruments detected that the solar wind was decelerating. Its speed dropped, and its structure became more complex. This was not a failure of the wind, but evidence of interaction. A brief teaching insight is helpful here. In physics, boundaries are often not created by solid barriers, but by competing pressures. The heliosphere is one such example. It exists because the outward pressure of the solar wind balances against the inward pressure of the interstellar medium. The result is not a rigid shell, but a vast, dynamic bubble surrounding the solar system. Its shape is not perfectly spherical. It responds continuously to changes in solar activity and the environment of the galaxy. This brings us to an important conclusion. Everything we consider part of the solar system exists within this bubble of influence. Beyond it lies a different regime, governed less by the Sun and more by the Milky Way. At the outermost limit of this structure, there exists a critical boundary where this balance finally shifts. That boundary will be the next step in our exploration. At the outermost limit of this structure, the balance between solar influence and the surrounding galaxy reaches a decisive point. This is where the outward pressure of the solar wind can no longer dominate. Instead, it yields. This boundary is known as the heliopause. In 2012, Voyager 1 became the first spacecraft to reach this region. What makes this moment scientifically significant is not the location alone, but the clarity of the measurements. The transition was not inferred indirectly, it was recorded through direct changes in the particle environment. As Voyager 1 approached this boundary, its instruments began to detect a sharp decline in particles originating from the Sun. At the same time, there was a noticeable increase in high-energy particles arriving from outside the solar system. These are known as galactic cosmic rays. Let us pause for a teaching insight. When two regions are governed by different sources of energy, their boundaries can often be identified by what dominates within them. In this case, solar particles defined one side, while cosmic rays defined the other. The shift between them was not gradual, it was distinct and measurable. This observation provided the first direct evidence that a human-made object had entered interstellar space. It is important to understand that this does not mean Voyager left the Sun's gravity. Rather, it moved beyond the Sun's energetic influence, which is a more meaningful definition in this context. Voyager 2 later crossed the same boundary, but along a different trajectory. Its data confirmed the same pattern, a drop in solar particles and a rise in cosmic radiation. This independent verification strengthened the conclusion that the heliopause is a real and consistent boundary, not a local anomaly. A useful comparison may help clarify this transition. Consider moving from a region dominated by one climate into another. The change may not be visible as a line on the ground, but instruments measuring temperature, pressure, and humidity will detect a clear shift. The heliopause functions in a similar way, defined by measurable conditions rather than visible markers. This leads us to an important realization. The boundary of our solar system is not theoretical. It can be detected, measured, and confirmed through observation. However, what scientists expected to find at this boundary was quite different from what Voyager actually revealed. That difference will guide our next step. What makes this boundary particularly important is not only that it exists, but that it behaves very differently from what scientists had predicted. Prior to Voyager's measurements, most models assumed that the transition between solar influence and interstellar space would be gradual. It was expected that particles from both regions would mix over a wide zone, creating a smooth and extended transition. However, the data told a different story. Instead of a broad region of blending, Voyager detected a boundary that was surprisingly narrow. The change in particle populations occurred over a relatively short distance. On one side, solar particles dominated. On the other, galactic cosmic rays became the defining feature. This observation is significant because it challenges a common assumption in space physics. We often expect that in low-density environments, such as space, transitions will be diffuse and extended. Yet here, we observe the opposite. The boundary behaves more like a distinct interface than a gradual gradient. A useful comparison can help clarify this. Consider the boundary between two fluids that do not mix easily, such as oil and water. While both are liquids, they maintain a clear separation under the right conditions. In a similar way, the solar and interstellar environments maintain their identity across the heliopause, rather than blending seamlessly. A teaching insight emerges here. Boundaries in physics are often defined not by physical walls, but by changes in dominant conditions. In this case, those conditions include particle origin, energy distribution, and magnetic influence. When these change rapidly, the boundary appears sharp, even in a region as sparse as interstellar space. The measurements also suggest that the heliopause has an internal structure. It is not simply a dividing surface, but a region with its own physical properties. The sharpness of the transition indicates that forces at this boundary are organized and stable enough to maintain separation. This forces a revision of earlier theoretical models. Scientists must now account for mechanisms that can produce and sustain such a defined interface under extremely low-density conditions. This includes interactions involving magnetic fields and plasma behavior, which are not always intuitive. The key conclusion is clear. The edge of the solar system is not only measurable, it is structured. It behaves more like a boundary with defined properties than a vague transition zone. And within this structured boundary, Voyager detected something else. A region where energy builds in unexpected ways, revealing that this interface is not passive, but physically active. Within this sharply defined boundary, the environment reveals another layer of complexity that was not anticipated. Just inside the heliopause, Voyager detected a region where the behavior of solar particles changes in a very specific way. They do not simply stop or pass through. Instead, they slow down, compress, and accumulate. This process leads to the formation of a high-energy plasma region. Plasma, as you know, is a state of matter where particles are ionized, meaning electrons are separated from nuclei. In this region, both the density and the energy of particles increase significantly compared to what was expected. Let us consider a simple analogy. When a flowing stream of water encounters a barrier, the water does not immediately stop. It builds up, slows, and becomes more turbulent. A similar effect occurs here, though governed by electromagnetic forces rather than fluid mechanics. The solar wind, meeting resistance from the interstellar medium, begins to pile up just before the boundary. Voyager's instruments recorded temperatures in this region that were far higher than earlier models had predicted. Particle densities were also elevated. This combination indicates that energy is not simply dissipated at the boundary. It is redistributed and concentrated. A teaching insight is useful at this point. In many physical systems, boundaries are not passive separators. They are active regions where energy transformations occur. The area just inside the heliopause is one such region. It converts kinetic energy from the solar wind into thermal and electromagnetic energy within the plasma. This discovery forces a refinement of how we understand the interaction between the solar wind and the interstellar medium. It is not a simple collision or gradual blending. It is a dynamic process involving compression, heating, and energy exchange. Another important point emerges from these observations. The existence of this energetic layer suggests that the heliosphere is not merely a region of influence, but a system with internal structure. Different zones within it behave according to different physical conditions. This has broader implications. If energy is concentrated near the boundary, it may influence how particles are transported, how magnetic fields behave, and how radiation propagates through this region. The key conclusion is that the boundary of the solar system is not quiet. It is an active region where measurable physical processes are continuously taking place. This realization naturally leads to a deeper question. If this boundary is so active, what role does it play in protecting the solar system from the much harsher environment beyond it? This realization naturally leads us to examine the function of this boundary more carefully. If energy is concentrated and interactions are active near the heliopause, then its role cannot be limited to separation alone. It must also influence what is allowed to pass through and what is not. The evidence from Voyager confirms this. As the spacecraft crossed the heliopause, one of the most noticeable changes was in radiation levels. Inside the heliosphere, the intensity of galactic cosmic rays was relatively lower. Beyond the boundary, that intensity increased sharply. This observation reveals an essential property of the heliosphere. It acts as a protective system. The solar wind, along with the magnetic fields carried by it, forms a barrier that partially shields the inner solar system from high-energy particles originating outside. To understand the importance of this, consider the nature of galactic cosmic rays. These are not ordinary particles. Many are accelerated by extreme astrophysical events such as supernova explosions. Their energies are so high that they can travel across vast distances of the galaxy at speeds approaching that of light. A teaching insight may help here. Protection in space is not achieved by solid walls, but by fields and flows. The heliosphere functions in a similar way to a magnetic shield. It does not block all incoming particles, but it reduces their intensity and alters their paths. Voyager's measurements provide direct evidence of this filtering effect. The sharp increase in cosmic radiation beyond the heliopause indicates that the inner region is comparatively shielded. This difference is not theoretical. It is measurable and consistent across both Voyager missions. This has important implications. The planets within the heliosphere, including Earth, exist in an environment where exposure to high-energy cosmic radiation is moderated. Without this protective influence, radiation levels would be significantly higher. It is also important to recognize that this shielding is not absolute. Some cosmic rays still penetrate the heliosphere. However, the reduction is enough to influence long-term conditions, including atmospheric chemistry and potential biological effects. Another point deserves attention. The effectiveness of this shielding depends on the strength of the solar wind and the structure of the heliosphere. As solar activity changes, so does the level of protection. This brings us to a deeper layer of complexity. If the boundary can filter and modify radiation, then its internal structure and the forces that shape it become critically important to understand. And it is precisely within this structure that Voyager revealed an unexpected behavior, one that challenges existing ideas about how magnetic fields interact at the edge of the solar system. If this boundary can filter radiation and sustain energetic processes, then the behavior of magnetic fields within it becomes a critical factor. Before Voyager reached this region, scientists had a clear expectation. The Sun's magnetic field, carried outward by the solar wind, and the magnetic field of the galaxy were thought to meet at noticeable angles. This difference was expected to create turbulence, distortion, and a complex pattern of field lines. Such a scenario would resemble two flowing systems colliding at different directions, producing instability and chaotic interactions. From a theoretical standpoint, this was a reasonable assumption. Magnetic fields embedded in plasma are highly sensitive to direction and motion. However, the measurements from Voyager did not support this expectation. Instead of a sharp change in direction across the heliopause, the magnetic field on both sides appeared more aligned than anticipated. The orientation did not shift dramatically as the spacecraft crossed into interstellar space. This observation introduces an important question. If the fields originate from different sources, why do they appear so similar at the boundary? A teaching insight can clarify the significance of this. Magnetic fields in space are not isolated structures. They can stretch, connect, and reorganize through processes such as magnetic reconnection. When this happens, field lines from different regions can link together, forming a more continuous configuration than previously assumed. Voyager's data suggests that something along these lines may be occurring near the heliopause. Rather than acting as a point of conflict between two separate magnetic systems, the boundary may allow for a degree of continuity or restructuring. This has important implications. If magnetic fields are more aligned, the way particles move across the boundary could be influenced. Charged particles tend to follow magnetic field lines. A smoother alignment may allow certain particles to travel more easily between regions, while still maintaining overall separation in terms of energy and origin. Another point to consider is stability. A highly turbulent boundary would produce fluctuating conditions, yet the observations indicate a level of consistency. This suggests that the magnetic configuration at the edge of the heliosphere is more stable than expected. The key conclusion is that magnetic interactions at this boundary are not chaotic in the way earlier models predicted. They are structured, possibly interconnected, and governed by processes that are still being studied. This naturally leads us to examine the environment beyond the boundary itself. If the magnetic behavior is unexpected, then the properties of the surrounding interstellar medium may also differ from prior assumptions. If the magnetic behavior at the boundary challenges expectations, then it becomes necessary to examine the external environment applying pressure on this system. The heliosphere does not exist in isolation. It is continuously shaped by the properties of the interstellar medium surrounding it. Voyager's measurements provided a key insight in this regard. The density of the interstellar medium was found to be higher than earlier estimates had suggested. This may seem like a small correction, but its implications are significant. Even a slight increase in density, when applied over vast distances, results in a measurable pressure acting against the heliosphere. To understand this, consider a simple example. If you inflate a balloon inside a room, the air pressure outside the balloon determines how large it can expand. Increase the external pressure and the balloon compresses. Reduce it, and the balloon expands further. The heliosphere behaves in a similar way. though governed by plasma physics rather than air pressure. A teaching insight is useful here. In space, structure is often determined by balance. The outward pressure of the solar wind pushes against the inward pressure of the interstellar medium. The shape and size of the heliosphere are defined by this equilibrium. Because the external pressure is not uniform, the heliosphere does not form a perfect sphere. Voyager data suggests that it is compressed in certain directions and extended in others. This creates an irregular, evolving shape rather than a stable geometric form. Another important point follows from this observation. As the Sun moves through the Milky Way, it encounters regions of varying density within the interstellar medium. This means the heliosphere itself is not constant over time. Its size and structure can change depending on the surrounding galactic environment. This introduces a dynamic perspective. The boundary of the solar system is not fixed in space. It responds to both internal forces such as solar activity and external forces from the galaxy. A brief example may clarify this further. If the Sun were to enter a denser region of interstellar space, the increased pressure would compress the heliosphere. If it moves into a less dense region, the heliosphere would expand. These changes occur over long timescales, but they are physically real and measurable. The key conclusion is that the solar system's boundary is shaped not only by the Sun, but also by the galaxy itself. It is the result of continuous interaction between local and external forces. This understanding moves the discussion beyond structure alone. It raises practical questions about how such changes might influence conditions within the solar system, particularly for future exploration beyond Earth. This understanding naturally shifts the discussion from structure to consequence. If the boundary of the solar system regulates radiation, evolves with galactic conditions, and contains active physical processes, then it directly affects any attempt to move beyond it. One of the most immediate concerns is radiation exposure. High-energy cosmic rays, which we have already identified as increasing beyond the heliopause, pose a significant challenge for human space exploration. Unlike lower-energy particles, these rays can penetrate spacecraft shielding and interact with biological tissue at the cellular level. Voyager's measurements provide a crucial reference point. By comparing radiation levels inside and outside the heliosphere, scientists can estimate the degree of protection this boundary offers. This allows for more accurate modeling of the conditions astronauts would face during long-duration missions. A teaching insight is useful here. In engineering, risk is often managed not by eliminating a hazard, but by understanding it precisely. The data from Voyager transforms cosmic radiation from an abstract threat into a quantifiable factor. This is essential for designing future spacecraft, habitats, and protective systems. Another implication extends beyond immediate missions. The heliosphere itself is not constant. As the Sun moves through the Milky Way, it encounters regions of varying density and pressure. These changes can alter the size and effectiveness of the heliosphere over time. Consider a simple scenario. If the solar system enters a denser region of interstellar space, the heliosphere may compress. This would reduce its ability to deflect incoming cosmic rays, increasing radiation levels throughout the system. Conversely, in less dense regions, the heliosphere may expand, offering greater protection. This introduces a long-term perspective. The environment of the solar system is not fixed across millions of years. It evolves as the Sun travels through the galaxy, carrying the planets with it. The conditions experienced by future generations may differ from those we observe today. These insights also influence mission planning. Routes, shielding requirements, and duration of exposure must all account for variations in radiation levels. Even robotic missions benefit from this knowledge, as electronic systems are also vulnerable to high-energy particles. The key conclusion is that the boundary we have been examining is not only a scientific curiosity, it is a factor that directly shapes the feasibility and safety of exploring space beyond Earth. This naturally leads to the next step. If these discoveries have already transformed our understanding, what might future missions reveal when they are designed specifically to study this region in greater detail? This naturally leads us to consider what these discoveries represent in a broader scientific context. The Voyager spacecraft were not designed as interstellar probes in the modern sense. Their instruments reflect the technology of more than 4 decades ago. Yet despite these limitations, they have provided direct measurements from a region that had previously existed only in theoretical models. What makes this achievement particularly important is not just the data itself, but the shift in perspective it creates. For the first time, the space beyond the heliosphere is no longer an abstract concept. It is a measurable environment with identifiable properties, including particle composition, magnetic behavior, and energy distribution. Engineers continue to manage the limited power available on these spacecraft with great care. As onboard systems are gradually turned off to conserve energy, priority is given to instruments that can still return meaningful scientific data. Each transmission, though increasingly faint, carries information from a region no spacecraft had ever directly sampled before. A teaching insight is worth noting here. Scientific progress often depends not on perfect instruments, but on persistent observation. Voyager demonstrates that even with aging technology, carefully collected data can reshape fundamental understanding. Another important point emerges from this ongoing mission. The boundary we have examined throughout this discussion is not defined by a physical object such as a planet or a belt of material. It is defined by a change in conditions, particularly magnetic and energetic properties. This redefines how we think about edges in space. They are not always visible or tangible, but they are real in terms of physics. Beyond this boundary lies the interstellar medium, shaped by the larger structure of the Milky Way. It is not empty, nor is it uniform. It contains variations in density, magnetic fields, and particle populations that influence how our solar system interacts with the galaxy. A brief example may help clarify this shift in thinking. Earlier, exploration meant observing distant objects through telescopes. Now, it includes directly sampling the space between stars. This transition marks the beginning of a new phase in space science. The key conclusion is clear. Voyager has transformed the idea of the solar system's edge from a distant assumption into a measurable boundary, and it has opened access to a new domain of study. For the first time, humanity is not limited to observing interstellar space from afar. It is actively measuring it, one signal at a time, extending our understanding beyond the limits that once defined our place in the universe.